Okay, in this video, we're going to be having a look at stationary points. What are they and what's the most basic way to be able to find them? Well, in essence, a stationary point is any point on a graph that has a gradient of 0. So, switch colors. If I have a standard quadratic graph, y equals x squared, well, here I'm going to have quite a strong negative gradient, say, minus 10. Here, maybe minus 5. Here, maybe minus 3. And eventually, it's going to turn positive. Now I'm going upwards. So I may have a gradient of 3, 5, 10 here, which means at the bottom here, at this kind of turning point, we're going to have a stationary point. So, as I kind of just mentioned, turning point, stationary point, they are the same thing, but there are a couple of other examples of stationary points as well that aren't necessarily turning points. But in essence, it is simply a point on a graph that has a gradient of 0. Now, there are 3 distinct types of stationary points. There is a local maximum, a local minimum, and a point of inflection. So, what do each of these mean? Well, a local maximum, as the name alludes to, is a stationary point that is at a maximum point in a curve. So, the curve goes up and up and up, hits a maximum point, and then comes back down. The reason it's called a local maximum is because, imagine I had a graph that looked like this. This point here would be considered a local maximum. Now, it's not the maximum of the graph, that would be up here. But locally, within its region, it is the maximum point. So this here would be a local maximum. So would that, and so would that. Now, a local minimum, as you can probably work out, is exactly the same thing, but opposite. Instead of it being the maximum point of a graph, it is the minimum point. Graph gets lower and lower and lower, hits a minimum and comes back up. Once again, the word local, because the graph could look like this whole thing joined together. And even though this here is the true minimum point of the graph, this is still locally within its little area a minimum. A point of inflection are neither of these. A point of inflection is a point on a graph that has a gradient of 0, so it's still a stationary point, but it doesn't necessarily look like a maximum or a minimum, because it's not. Now, what a point of inflection looks like, there are 2 kind of key examples, one of which would be this. Here I've got a graph where in the middle I have a nice horizontal section. And a horizontal part of a graph has a gradient of 0. But it's not a maximum, right? Because it gets higher after it. And it's not a minimum because it's lower before it. So this here is a point of inflection. It can look like that, or it can look like that. It is simply a point that has 0 gradient, so a straight line without having the properties of a local minimum or maximum. Fairly straightforward. So now let's have a look at how to find out what a stationary point is, whether it is a maximum, a minimum, or a point of inflection. Okay, to kind of explain this, let's have a look at this graph here, which has a stationary point up here, which is a local maximum. Now, imagine the graph was a little bit more complicated, or I didn't have the ability to draw it, so I didn't have a fancy calculator, or for some reason I didn't want to use it. How would I know that this is a local maximum if I just had the equation y equals minus x squared? So I just had the equation of the line, how would I know? Well, in order to answer that, we need to kind of zoom in. If I zoom in on this graph, I get something that looks like this. right? That's just the top of it zoomed in with my point of, my local maximum, my stationary point just there. And what we want to do is we want to have a look at either side of my stationary point. So on the left, the graph is going up, 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 right? Even though it's, smooth, it's not a straight line, it's still increasing. And if it's increasing, it's going to have a positive gradient. Then we hit our point, and after it, it goes down, 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 down. Again, I know it's curved, but just to illustrate, it's going down, which means it has a negative gradient. So what we can do is once we've found our stationary points, and at our stationary point, dy dx, where let's say my stationary point is at x coordinate A, my gradient at x equals A is 0. However, to the left of it, so let's say a distance h away from the centre, my dy dx, where x equals A minus h, is going to be positive. And similarly, on the other side, let's say A plus h, just a tiny little distance away, x equals A plus h, my gradient is going to be negative. So I can take a point either side of my stationary point. I can determine if the gradient is positive or negative, and using that information, I can determine if it is a local maximum, a local minimum, or potentially a point of inflection. Now, this is just one method of how to do it. In the next video, I'll show you the next one using higher order derivatives. But just to quickly go over it a little bit more before I give an example, if we did this process and we found on the left of my stationary point is a positive gradient and on the right it is negative, then this is going to be a local maximum. I always like to draw it. If you just draw a positive line and then a negative line, we can see our point is a maximum. Conversely, if it goes negative and then positive, well, I have got a minimum. If it goes positive and then positive again, that is going to be a point of inflection. And if it's negative and then negative again, it is also going to be a point of inflection. So this is what we're on the lookout for. What's happening to the gradient just to the left of my point and just to the right of my point? Okay, let's do one example to finish this off. Okay, for our example, I've got this horrible looking polynomial function here. I've got f of x is 3x to the 4 minus 8x cubed minus 6x squared plus 24x plus 20. And we are going to try and find out, let me just redo that because that does not look like a 3, all of the stationary points on this curve or on this graph. So how do we do that? How do we get to the stationary points first? Well, we know that at a stationary point, the gradient, so dy dx, is going to equal 0. So let's start off by differentiating this. 3x to the 4 is going to become 12x cubed minus 24x squared minus 12x plus 24. And this here is equal to 0. So I want to solve this thing here equaling 0. Okay, right. First thing I notice is I've got a multiple of 12 in every component, so I'm going to factor that out. 0 equals 12, x cubed minus 2x squared minus x plus 2. Now, from here, of course, you could just throw all this into your calculator and you get the same result. From here, I'm looking on how to factor this out. I probably recommend doing a calculator, but I think I can factor out an x minus 1, and then that will give me x squared minus x minus 2. probably shouldn't be doing this live. Yes, okay, yeah, that works, okay. So, I've got this whole thing here equaling 0. This then can be factored out slightly easier into x minus 2 and x plus 1. And now I can see that my possible values for x, when all this is equal to 0, are 1. So x equals 1, 2, and -1. So my stationary points on this curve, the point at which my gradient is 0, are at the points x equals 1, 2, and -1. So now it's a case of using these to work out if they are maximums, minimums, or points of inflection. Now, first of all, I don't need to get the y coordinates for each of them. That's not really relevant. We're only going to be working with x. Of course, you could plug those into there and get your y's if you would like, or if the question requires it. But I'm not going to do that. What I'm going to do is I'm going to split this up into 3. First of all, my point of inflection when x equals 1. What exactly is this type of point? Well, first of all, I shouldn't have rubbed out my dy dx because I'm going to need to keep that. So let me quickly throw that back in. Minus 12x plus 24. That's my dy dx. Luckily, you don't have the issue of rubbing things out in your exam. And if you are rubbing things out in your exam, then you shouldn't. So there's my dy dx. And remember, I want to find a point just to the left and right of x equals 1. Because I want to determine if my gradient is positive or negative just before, and if it's positive or negative just after. So, the way that I'm going to do that is I'm going to choose numbers that are very, very close to 1. I'm not going to choose 0 and 2, or 0.5 and 1.5, just because I don't really know what's going on with the graph. It might end up having loads of little bumps in that area. So to get as close as possible, I'm going to choose 0.9 and 1.1. You could technically choose 0.999 and 1.001 if you wanted to, but 0.9 and 1.1 will be fine. So I'm going to pop my 0.9 into this equation, and I'm going to determine if it is positive or negative. And before I do that, I need to go and get my calculator, because I'm not doing that in my head. Honestly, you'd think I'd come prepared, but I haven't. So I'm going to pop 0.9 into my gradient to find out my gradient, my dy by dx at x is 0.9. So I get 0.9 cubed times by 12. I won't make you sit through all of this, I promise. Okay, and just like that, I find that 0.9 put into this gives me 2.508. The number's not important. What is important is that it is positive. So I can do a nice little line up here on the left. Then on the right, if I put 1.1 into this equation, I get minus 2.27. Again, the number's not important, but what is important is it is negative, meaning after my point to the right, it goes down, meaning my point is a maximum. So now I need to do the same thing for x equals 2 and x equals -1. So for x equals 2, if I choose 1.9 to the left and 2.1 to the right, then, okay, boring calculator work again, then I get that 1.9 put into here to the left of my point is minus 3.13. So it is negative. Again, don't care about the number, just care about the negative. Then my point, and to the right of my point, I have got 4.1, which is positive. So from my little sketch, it is a minimum. And then finally, for x equals -1, I'm going to choose minus 1.1 and minus 0.9. Just make sure you don't get confused with which is to the left and which is to the right. Draw a number line if you have to. So if I throw minus 1.1 into this equation, then I will get that minus 1.1 in there is minus 7.8, which is negative, So it looks like that. And minus 0.9 popped into my gradient gives me a gradient of 6.6, which is positive. So this final one here is a minimum.